Hello guys, welcome to this video. Recently I started working on my own Vulkan based game engine and editor. I think it would be interesting to make it as a devlog to motivate myself to keep on working it, and it may be interesting to people who are interested in related topics, and yeah, it can also be handy for my other graphics projects. Anyway, I decided to call the engine Hedge without too many reasons, just thought it is an interesting word. Yeah, let's start. So first, here's the GitHub repo of this project. You can find the link of this project in the description of this video. Besides, you can find the git clone and the cmake commands from the repo. And as you can see, it is a little bit complicated to set up since it's still at an early stage and you even need to set up the environment variables. So yeah, our first part of this video will introduce how to set up this project. So before using cmake to build the project, let's take a look at the prerequisites. This project needs Vulkan SDK, Python, cmake, Ninja, Visual Studio, and Windows SDK. By the way, it's possible to use other C++ development environment like C-Line or VS Code, but I prefer this way since it's more convenient to me. Then let's configure this project. First of all, let's build an empty folder, then clone the project into it. After finish, we can get into the editor folder and use cmake to generate our game editor's Visual Studio solution. After that, we can compile it and boom, it finishes. Now we can open this editor and see the default scene, which is created at the initialization stage of the editor. Here we can see a cube, a point light, and a camera that is similar to Unreal. As for the control of the camera, it is a little bit different from Unreal or Unreal's editor. It takes WASD as pen, and the mouse middle button is used to control the direction of the camera. Then let's take a look at how to use this editor to create and open a project and build or package a game in the project. So first, let's find the test folder created before and create as well as select a new folder in it. After selection, the editor stores the current information. Then let's change the position of the camera and reopen the project stored before. As you can see, the editor reads back the information stored before, like the position of the camera. Next, let's take a look at how to build the game out of the project. By the way, after we open a project, the upper left corner of the editor would show the name, and you can see that the name is changed from the empty project to the project name that we have now. Back to the build, we can find the build option in the menu bar, and we can select whether you want a release or debug version. For debug version, the editor would generate the Visual Studio solution of the game. So after a while, you can see that there is a build folder generated. So in this folder, we can find the game's solution. Now let's take a look at what happened. Under the hood, the editor generated a CMake file and used that to generate the solution. As you can see, the game itself relies on lots of things, and you can see that it includes the headers of the Hedge library as well as the static library file itself. So the Hedge library package consists of both headers and the static library object. Besides the Hedge underline lab here is an environment variable that points to the path of the engine package. In the future, I hope that I can make an installer to set up all these things, but now we have to set the environment variable manually. In addition to the Hedge engine.lib and its headers, it also has other third-party libraries like Vulkan.lab, GLFW, YAML CPP, and the editor itself. They are also manually copied here, which is the prepackaged engine. It's a little bit awkward, so I'll try to write up some scripts to facilitate. I know now is a little bit confusing, so I draw a diagram to show the software architecture here. Previously, we built the editor and there is an engine embedded into the editor. This embedded editor is just used to drive the rendering of the editor and the scene in the editor, which is not used to generate the game project. Instead, the game project links the game engine library in the pre-built package. By the way, the standalone game engine library is not built from the editor project. So let's take a look at how to manually generate the package and build the game that links the package. First, let's delete all the libraries here and regenerate them. Then stepping into the engine folder and input the CMake command, which just specifies the generator. The output Visual Studio solution is the project that only outputs the static libraries. Here you can see that these libraries are slowly generated, and it also needs the Vulkan-1.lib, so we copy and paste it from the Vulkan SDK. After all these chores, we can compile and run our game. Let's come back to the generated game project and hit compile and run. As you can see, we now have a game which has a camera, point light, and a cube. Until now, we have shown how to clone the project down and build the editor as well as the engine that it's based on. However, I want to make this engine more game developer friendly, which means people who want to use this engine don't have to build the editor and engine from scratch, and they can just use the editor to build games directly. As a result, I also packaged the engine and editor beforehand. Let's check the GitHub release and download the zip file. Here you can find the editor and engine library that I showed before, which is only used by the game. Let's download it and try the game developer workflow. As you can see, it just has the libraries, headers, and the executable that I showed before. As a game developer, you only need to double-click the editor and open it. Here is the default scene, and let's just open an existing project that we created before. You can see that the camera's position is set to the position stored in the project file. Then we can just use this project to release a game. Note that it's different from the debug game project that we built before. Here, we directly package the game without any project files. So the executable is just here, and let's double click it and we can get the default game. Then I want to introduce how did I design the engine and the important points that I hope I knew. It has 5 parts: the useful references, event system, serialization and deserialization, Vulkan perspective, metrics, derivation, and the entity component system. The first part is the good references that I hope that I knew before. I highly recommend the Chernal's Game Engine series. His videos introduce lots of useful and handy third-party softwares and the trend of the technology. For example, I planned to use JSON as my serialization and deserialization library, but he introduced the YAML CPP, which looks much better than JSON. Besides, he also introduced the entity component system and the NTT library. It makes me realize that I shouldn't use the object-centric system. Instead, I should use a component-centric system because it can significantly improve the performance during each frame's update. Except for Chernal's videos, I also referred the real-time rendering book, but it has too many theories and histories, which is not super useful. Next, let's talk about the event system. In general, it's a stream-based immediate event system, and everything is controlled by an event manager in Hedge. So when an entity is spawned in the scene, it registers an event through the event manager. In every frame, event manager sends event through the entity's own event function so that entity can react to the sent event. Now let's use the camera's fly movement as an example to understand how does the event system work. First, when an entity is defined, an event manager object is passed into the initialization function. This object is used to register the events that this entity wants to listen to. Then, in every frame loop, event manager dispatches I/O events through the send I/O event function. Under the hood, the event manager calls entity's own event function and send an event object to the entity. As a result, we can control the camera's movement by writing code in the camera's entity's own event function to parse the event object and react to the WASD keys. Then I want to introduce the serialization and deserialization. It basically means read and write information from disk. This system in Hedge bases on YAML CPP. So let's also use camera as an example. This is the release game that we built before. The game consists of all the files in this folder. Then let's come under the scene folder and open the test scene.yaml. Here we can see that this is our scene file. The game executable reads this file to generate the cube and the camera in the scene. As for code relating to serialization and deserialization, you can find them under the H serializer.cpp or H files. Besides, every components have its own serialization and deserialization functions so that they are customizable. Of course, it makes the definition of a new entity or component become a little bit complicated because we need to register every entity's serialization, deserialization, and initialization function. The register process happens in the H frame listeners register serialize class function. As you can see, currently we only have 3 default classes. As for custom entities, a game developer needs to override the register custom serialize class function and registers his or her entities in this function. The next thing that I feel tough is the Vulkan perspective matrix. I highly recommend people who are interested in this topic to read this article. It has informative derivation, and most importantly, you can just copy and paste the conclusion. Here I just simply introduce this article. Basically, perspective matrix is used to project the frustum in the picture 1 to the clip space. The frustum in the clip space becomes the NDC at right after the perspective division. By the way, Vulkan has a NDC different from OpenGL. In Vulkan, the center of the screen is 0, 0. The positive Y is pointing downward and the positive X is pointing at right. Generally speaking, the depth is from 0 to 1, but actually you can arbitrarily configure the NDC when you configure the Vulkan's pipeline. In this article, the author derives the mapping relationship for X, Y, and then derives the relationship for Z. Let's take a look at the XY derivation first. The illustration here introduces how to map an arbitrary point XY in the camera space to the near plane's XY. As you can see, the author uses the side view to demonstrate how to derive the Y due to parallel vertical lines and the alignment angles. The tangent of the angles between the point in the camera space and the mapped point on the near plane is same, and we also know the near plane's Z value. The Z value of the original point and Y value of the original point. As a result, we can just calculate the Y value of the mapped point on the near plane, and is in the camera space. So in order to get points in the NDC, we can just remap them to the -1 to 1. Similarly, we can derive the X value on the near plane from the top-down view. So we have 2 equations to map arbitrary points x, y in the camera space to the NDC space. And you can see that both of them are linear equations, so we can integrate them into a matrix. However, the perspective matrix doesn't have clip division and is only responsible for mapping a camera space point to the clip space instead of NDC, so we have to find out the perspective division factor. As for the derivation for z or depth is similar to what we have done, but the answer maps the far plane in the camera space to 0 and the near plane to 1 in order to make use of the precision in the float point number that stores the depths. This involves more specific details in this article, so I highly recommend you to read this. Next, I want to introduce the entity component system used in Hedge. It totally bases on this entity library. It's a component-centric entity management library. In other words, it doesn't store any entities. It only stores components. The entity in this is just a hash. We can query the components linked to a hash to see what components an entity has. In the code, we basically mimic this idea. When an entity is spawned, we will just call the onDefine entity function. In this function, we tell the entity system that we want to create components that belong to this entity. For example, our camera entity has a transform component and a camera component. Finally, I want to introduce my future plan. As you can see, the engine is still at a very beginning stage, but my goal is to use it to make a 3D game. And I want to record this process as a series of videos to share with you. Of course, there are lots of contents that I want to add, like Gizmo for the editor and graphics tech like spatial data structure, difframed rendering, and PBR for the engine. Well, I believe it will take some time since I have a full-time job. Well, anyway, I hope you enjoy this video and see you in my next video.